going to look more and more like a normal distribution. Right. So if all the samples end up miraculously being the same, but the whole theorem is based on all possible samples, so all combinations. Yeah. And then it will be a normal. So we'll see this theorem in action. Here it is right here. You draw a simple random sample, SRS, of size n from any population with mean mu and a finite standard deviation sigma. It has to be finite. Some exist that don't. The central limit theorem, though, says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. It won't be exact, but it will be good enough. It will be approximate. And so it will be normal with mean mu and standard deviation sigma over the square root of n. And the central limit then theorem, it allows us to use normal probability calculations, the tables, to answer questions about the sample means from many, many observations, even when a population distribution is not normal. So that's the remarkable part of it. So even, I think I've got some pictures here first. So you can see if the parent population distribution looks like A, really, really right skewed. If you take B is taking all possible samples, I think it was size 5, and then this was taking more samples and then taking even more samples from the population. It usually requires this is controversial, but usually you need to take at least size, I can't remember what our book is, 25 to 30. The sample needs to be size 25 or 30. I can't think of what the book uses. I think it uses, well, you guys can let me know. I think it's size 30. So all possible samples of size 30. If it's less than that, then the sampling distribution might not. So if your sample is less than 30 and your underlying distribution is not normal, then it might not be very accurate. So it needs to be at least size 30 for the central limit theorem to hold. If the population distribution, though, is normal, and you know for sure it's coming from, let's say, heights, and you know it's normal, then you can take a sample of size 2 if you want, or size 5. It doesn't matter. It will still automatically be normal. But if you're not sure then of what the population distribution looks like, then you need to take, let's go with 30, at least 30. I'll confirm that, though, for the next lecture, which is in 2 weeks, right? So I'll confirm. What would be a nice looking distribution of grades for this course, for the midterm grades? So would it be right skewed, left skewed? What would be good? Would it be good if it was right skewed? That would not be good, right? So what would be good if I was to plot all the grades? Yeah. 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 Left skewed. Yeah, an ideal from many perspectives is that, right? That would be ideal to have, right? A left skewed distribution. It would be quite nice, right? If the grades, because that would mean most people did really well. And so I have a simulation. Now, these are not the actual grades because I don't have everything marked, but an actual simulation where I have an average, I think I made the average something like 66. It would look like this. So this would be, oh, I got to change. I thought you guys were seeing this. Let me stop the share and get onto the software here. There. There we go. So I teach a computing course using R. Has anyone used R? I know there's one of your courses, I think you're going to be using R in psychology. Anyways, this is called R. We call it R or RStudio. and we use it for analyzing data. So this would be ideal if the grades look like that. This is just synthetic data. I'm just making it up, just random data. But that would be the distribution. And so let's say I take all possible, let's see if I take, yeah, so this is going to be the first one. So that, I just put like a curve on it. So this is the first one, and that's just the raw, we call those the raw grades or the individual grades, and it's the population. And I can calculate the mean of the population and the standard deviation. But if I take, let's say 100 samples of size 30, I get this. 100 samples of size 30 looks like that already. Just using 100, that's only 100 samples. So what I did is I take 30 students, calculate the mean, and store it, and then put it back, and then randomly select another 30 students, calculate the mean, store that, and put them back, and keep doing that 100 times. So 100 samples, 100 sample means n equals each one size 30. So let's keep going. Let's try 1,000. And it's already looking even better. And you can see the variability is changing. Notice how I'm going from left skewed. This is the central limit theorem in action. Just taking those, I'm taking now 1,000 sample means each size 30. So I have 1,000 X bars. And you can see that I'm converging on the simulated population, which had a mean of 66. That's an average 66 score. And you can see it's starting to really converge with that. Yeah. No, actually, quite often we see bimodal. We usually with grades. So sometimes it will come out like this, but sometimes we see this. This is really common with grades. So we have this, and we'll see this like that. We usually see two groups of students. The group that was really prepared, and then the group that wasn't so prepared. So that happens. Very rarely do we see a normal distribution of grades. Because that would mean, if you think about the shape, right, that would mean only a few got really high and a few got really low. Where usually it's the bulk gets usually in the 60s, 70s in there. If it's bimodal, yeah, you can't use it. Yeah, it runs into trouble because you would want to do it separately for the low grades and one, so you would want to stratify the class into two, low, high, and then do it that way. Then this would all work. So I'm going to keep going. I'm going to do another one where we get 10,000 sample means right here, 10,000 sample means, all size 30. Now look at that. It's really becoming less variable than that. I'm predicting the midterm grades will look something like that. Probably, but I don't know. I haven't got any preliminary. And here is 100,000 sample means. Like that. And then it takes a few minutes. I'm running 1 million. It just takes a few minutes. You can see the stop sign. So it just takes a couple minutes to run 1 million because what it's doing is it's taking from the midterm grades, that first one, that population, it's taking 30, calculating a mean, and it's doing that repeatedly for 1 million times.